Hello students, welcome to our new video presentation of Unit 1 Part 2 titled Some Basic Concepts of Chemistry. You know very well that we are covering this lecture based on NCERT syllabus which was rationalized for the year 2023-24. In today's session, we will talk about Section 1.3, that is properties of matter and their measurement, and as well as Section 1.4, uncertainty in measurements. Please note down all the important points as the same will help you in answering questions in your academic as well as competitive examination. I welcome you once again. Properties of matter and their measurement. Every substance has a unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acid and bases, etc. Thus, every substance has unique or characteristic properties. These properties can be classified into two categories. Physical properties. Physical properties can be measured or observed without changing the identity or composition of the substance. The physical properties are associated with physical existence of matter. Physical properties can be classified without changing the composition. Example, color, odor, melting point, boiling point, density, etc. Measurement of physical properties does not require occurrences of chemical change. Chemical property is the ability of a substance to form new substances, either by decomposition or by reaction with other substances. Example, acidity, basicity, combustibility, etc. The measurements or observations of chemical properties require a chemical change to occur. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will study about measurement of physical properties. Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by its unit in which it is measured. For example, if you want to measure the length of a room, say 6 meter room, 6 meter, that is 6 meter represents the length of the room. Here it is written as 6m. Here 6 is the number and m denotes meter, the unit in which the length is measured. So m is the length, and symbol is m, small m. The international system of units. The international system of units, which is spoken or written in French language as Le Système International des Units, abbreviated as SI. That is, SI represents international system. The international system of units was established by the 11th General Conference on Weights and Measure. It is called a CGPM, from Conference Générale des Poids et Measures, which is a French language for CGPM. The CGPM is an international treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in the year 1875. The SI system has 7 base units and they are listed in Table 1. These units pertain to 7 fundamental scientific quantities. The other physical quantities, such as speed, volume, density, can be derived from these units. In India, the National Meteorology Institute, written as NMI, maintains standards of measurements. National Physical Laboratory, that is NPL, New Delhi, establishes experiments to realize the base units and derived units of measurements and maintains national standards of measurement. So, national standards of measurement are kept in NPL New Delhi. These standards are periodically intercompared with standards maintained at National Meteorology Institute in the world. That is, the Indian national standards are compared with the international studies, international measurement, and these are done by National Physical Laboratories. These are also compared with the International Bureau of Standards, whose headquarters is in Paris. Mass, weight and volume. The first we will discuss about mass and weight. Mass of a substance is the amount of matter present in the substance and is measured very accurately in the laboratory by using an analytical balance. The mass of a substance remains constant everywhere. That means it does not vary from place to place or location to location. The SI unit of mass is kilogram. However, smaller amounts of chemicals are used in chemical reactions, and we use very frequently the fraction of kg named as gram in the laboratories. That means the fraction of kg is a gram and 1 kg is equal to 1000 gram. As against mass, weight is also used. Weight is the force exerted by gravity on object. That is, weight W is equal to mass into gravity, G, gravitational force. Weight may vary from one place to another due to change in gravity. Next is volume. Volume is the amount of space occupied by a substance. It has units of length cube. That is, the units of length are length into breadth into height. Hence, each length is represented by m, and m to the power of 3 is used for volume. In SI system, volume has units of m to the power of 3. But again, in chemical laboratories, smaller volumes are used. Hence, volume is often denoted by Cm to the power of 3 or dm to the power of 3, that is decimeter cube units. Please see the figure shown on screen. Here we have shown the different units used to express volume. Here the smallest unit is 1 centimeter shown in the screen, and the total volume of the cube is 10 centimeters, that is equal to 1 decimeter. A common unit to measure volume of liquid is a liter, represented by letter capital L, which is not an SI unit. So the SI unit for volume is length to the power of 3, but not liter. 1 liter is equal to 1000 milliliters. That is 1000. 1 liter is 1000 centimeter cube is equal to 1 decimeter whole cube. In laboratories, volume of liquids or solutions is measured by graduated cylinders, burette and pipette, etc. These are shown in the figure on the right hand side of your screen. Some volume measuring devices are shown here. The first one, the top left one, is a burette. The next one is pipette. The second one is pipette. The third one is a graduated cylinder. And the fourth one is volumetric flask. These are different types of graduated instruments, graduated measuring devices used for measuring the volume of liquids or solutions. These are called burette, pipette, graduated cylinder and volumetric flask. A volumetric flask is used to prepare a known volume of solution. The measuring devices are shown in figure number 2. In this slide, we will take up section 1.3.6 and 1.3.7. 1.3.6 covers density. The two properties, mass and volume, are related to density as density is equal to mass over volume, or it can be said that density of a substance is its amount of mass per unit volume. Therefore, density is equal to mass per volume. In SI units, SI unit of density is kgs per meter cube, or it can be calculated as the SI unit of density is equal to SI unit of mass divided by SI unit of volume. That is, SI unit of mass is kg and SI unit of volume is meter cube. So therefore, the SI unit of density becomes kg per meter cube or kg m to the power of minus 3. This unit is quite large and chemists often express density in grams per centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how close its particles are packed. If the density is more, it means the particles are more closely packed. Next is temperature. There are three common scales to measure temperature. Degrees Celsius, written as degree C, degree Fahrenheit F, that is degree Fahrenheit, and Kelvin. Please note there is no degree sign in writing while writing Kelvin. Here K is the SI unit. So SI unit of temperature is Kelvin, whose symbol is capital K. The thermometers based on these scales are shown in the figure. The first thermometer is Kelvin, the second one is Celsius, and the third one is Fahrenheit. This is Fahrenheit. Please note here it is K Kelvin, it is C Celsius, and this is F. Generally, the thermometer with Celsius scales are calibrated from 0 to 100. You please see here the calibration between 0 to 100. 0 is the ice point and 100 is the steam point, where these two temperatures are the freezing point and boiling point of water respectively. The Fahrenheit scale is represented between 32 degrees and 212 degrees. You see here when this is said Celsius scale is 0, the Fahrenheit scale is 32, and when Celsius scale is 100, the Fahrenheit scale is 212. The temperatures on two scales are related to each other by the following relationship. The Fahrenheit scale, Kelvin scale, is related to Celsius scale as given below. First, between Fahrenheit and degree Celsius. 0 Fahrenheit is equal to 9 by 5 degrees Celsius. That is, degree Fahrenheit is equal to 9 by 5 degrees Celsius. Therefore, Kelvin will be equal to degree Celsius plus 273.15. There is another formula for explaining the relationship between temperature in Fahrenheit and temperature in centigrade. This will be helpful in converting Fahrenheit into Celsius. So Tf minus 32 divided by 180 is equal to Tc divided by 100. It is interesting to note that temperatures below 0 degrees Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale negative temperature is not possible. As you know, the SI system has 7 base units and they are listed in the table number 1 shown on your screen. These units pertain to 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these units. The 7 base units are in SI system are length, mass, time, electric current, temperature, amount of substance, and luminous intensity. These are the 7 base quantities of physical quantities or fundamental scientific quantities. The first one is length, second mass, time, electric current, temperature, amount of substance, and luminous intensities. The names of The units are meter, represented by symbol m, is used for measuring the length. The unit for mass is SI unit for mass is kilogram and it is kg. Its symbol is kg. The unit of time is second and its symbol is small s. The unit of measuring electric current is ampere with capital A as its symbol. The unit of temperature, SI unit of temperature is Kelvin and its symbol is capital K. The unit to measure amount of a substance is mole and its symbol is mol, M-O-L, mol. And the unit of luminous intensity is candela and the symbol for luminous intensity is small c, small d, candela. The definitions of each of these quantities is also shown on your screen. These definitions you please go through for once. These are measured or standardized in terms of other quantities, measurable quantities like speed of light for length, and it is Planck's constant for mass. The time is defined in terms of cesium frequency delta VCS. Electric current is defined in terms of charge E and its value is also given. The temperature is defined in terms of Boltzmann constant, whose value is also given on the screen. The amount of substance is measured in terms of, is standardized in terms of Avogadro constant Na. And finally, the luminous intensity is defined by fixed numerical value of luminous efficacy of monochromatic radiation frequency. You need not remember the definitions because these will not be asked. But however, you should know how these basic quantities are defined in SI units, SI system. The table 2 shows the SI prefixes and symbols used in chemical laboratories. These prefixes are the factors like when the measuring very high quantity, it is 10 to the power of 18, that is exa, 10 to the power of 15 peta, and 10 to the power of 12 tera, 10 to the power of 9 is giga, 10 to the power of 6 is mega, and 10 to the power of 3 is kilo. 10 to the power of 2 is hecto and 10 to the power of 1 is deca. And these symbols are also given, that is EP for peta, T for tera, capital T for tera, and giga, capital G for gera, and giga, and capital M for mega, and small k for kilo. Similarly for others. For smaller, that is minus quantities, negative quantities, a very small 10 to the power of minus 18 is atto and its symbol is small a. Please note that we use for positive powers, that is superscripts, we use capital letters except one or two. For kg and deca, we use majority in small symbols. Atto, 10 to the power of minus 15 is femto, small f. And pico is 10 to the power of minus 12, pico, small p. And 10 to the power of minus 9 is nano, that is small n. And 10 to the power of minus 6 is micro, that is Greek letter mu is used. 10 to the power minus 3 is milli, and its symbol is small m. 10 to the power of minus 2 is centi, that is c, small c. 10 to the power of minus 1 is deci, small d. Very frequently, we are using this in tera, giga, mega, and kilo, as well as pico for measuring capacitance, nano, micro, and millicenti. You have to remember and use them. Next, we will know about some units retained for general use. These units shown on the screen are used, and these are outside the international units, that is IS system, SI system. So name is minute. So those seconds is used, minute is used in outside the SI unit very frequently, and hour also we are using in our day-to-day life. Day is day also 24 hours. So minute is 60 second and hour is 60 minute, that is equal to 3600 seconds. Day is 24 hours. So if you convert a day into seconds, it is 86,400 seconds. Year is 365.25 days, and that is equal to 3.156 into 10 to the power of 7 seconds. Degree is 1 degree is equal to pi by 180 degrees radians. So instead of degree, we can use radians also. Liter also we have defined. 1 ton is equal to 10 to the power of 3 kgs. 1 carat is equal to, that is used carat we are using for measuring gold, 200 milligrams. Bar is the atmospheric pressure, and sometimes we use the words MPa or 10 to the power of 5 Pa. Curie is Ci, and Roentgen is R. Quintal is Q, that is 100 kg. Born is 100 Fm square, or 10 to the power of minus 28 m square. Air is small a, 1 dA, that is decameter square. Decameter square, 10 square meter square. Hectare HA, 1 hm square is equal, hectometer square is equal to 10 to the power of 4 meter square. Standard atmospheric pressure, we use the symbol ATM, atmosphere, and that is also expressed in terms of pascals. Uncertainty in measurements. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to extent possible. These ideas are discussed in this slide. Scientific notation. As chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers. Large numbers, a chemist has to deal with numbers as large as the figures shown in the figure. That is 602 divided 602 comma 200 comma 3 zeros, 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 and comma 3 zeros, just for the molecules of 2 grams of hydrogen. Similarly, the case of small numbers shown on the screen for a mass of hydrogen atom. And another examples of such small numbers or values are the constants, such as Planck's constant, speed of light, charges on particles, etc., involve numbers of the varied magnitude, very large or very small. It offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication, and division of such numbers. This problem is solved by using scientific notation for such numbers. That is, we use exponential notation in which the number is expressed as capital N into 10 to the power of small n, where small n is the exponent having positive or negative values, and capital N is a number called digit term which varies from 1.000 and 9.999 followed by any digit. Thus, we can write 232.508 as 2.32508 into 10 to the power of 2. That is, we have shifted these digit at the decimal place to left after first digit 2.32508 into 10 to the power of 2 in scientific notation. This is scientific notation when we are using exponential notation. Similarly, another number 0.3016 can be written as 1.6 into 10 to the power of minus 4. That is, we have shifted the digit to 4 places on the right hand side and we have written 10 to the power of minus 4. Here the decimal has to move 4 places to the right and minus 4 is the exponent of the scientific notation. Now let us do some addition, subtraction, multiplication and division quickly. 6.64 into 10 to the power of 4 and 8.95 into 10 to the power of 3 can be written as 6.65 into 10 to the power of 4, and here shifting the decimal place to the left and adding one exponential. So 0.895 into 10 to the power of 4. So that becomes 7.45 into 10 to the power of 4. You please write this and practice how to shift the digits and increase the number of exponent. The next example is subtraction of two digits. Two numbers 2.5 into 10 to the power of minus 2 minus of 4.8 into 10 to the power of minus 3. So this can be written as 2.5 into 10 to the power of minus 2 minus of, here shift the digit to the left. So it can be written as 0.48 into 10 to the power of minus 2. So when we shift it, this number, the exponent decreases by 1. So that is written 2.5 in minus 0.48 into 10 to the power of minus 2. Here we are writing 10 point minus 2 all both the digits because we have to take the common, taking it as common. So that becomes 2.02 into 10 to the power of minus 2. The third one is multiplication. Let us take the example. Multiply 5.6 into 10 to the power of 5 into 6.9 into 10 to the power of 8. So that becomes the first term as it is 5.6 into 10 to the power of 5 into 6.9 into 10 to the power of 8. So we will take out these two numbers as it is and the exponent will write as 10 to the power of 5 plus 8 using the basic principles of exponential algebra. So that becomes 38.64 multiplying into 10 to the power of 5 plus 8 is 13. So that can be written shifting the digit left side. It is 3.864 into 10 to the power of 14. Next example, another example, 9.8 into 10 to the power of minus 2 into 2.5 into 10 to the power of minus 6. Here we write 9.8 and 2.5 as it is and we add here 10 to the power of minus 2 plus minus of 6. That becomes minus 8. 24.5 into 10 to the power of minus 8. We want digit one, single digit here. So we make it 2.4 into 4, 2.450 into 10 to the power of minus 7. Division example 2.7 into 10 to the power of minus 3 divided by 5.5 into 10 to the power of 4. Here we divide 2.7 by 5.5 into 10 to the power of minus 3, and we move this exponent in the new denominator to numerator, and the sign changes, it becomes minus 3 minus 4. So if you divide the answer for 2.7 divided by 5.5 is 0.4909 into 10 to the power of minus 7, or it can be written moving the digit to right hand side, it can be written as 4.909 into 10 to the power of minus 8. That is the answer. Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurements. The digits whose values are accurately known in particular measurement are called its significant figures. Larger the number of significant figures, greater will be the accuracy in measurement. There are certain rules for determining the number of significant figures. These are listed below. Rule number 1. All non-zero digits are significant. For example, in 285 centimeter, there are three significant figures, and in the number 0.25 milliliter, there are two significant figures. All the zeros between two non-zero digits are significant. Say for example, 2.005 has four significant figures. 2005. There are four significant figures. Leading zeros to the left of non-zero numbers are not significant. Such zeros indicate the position of decimal point. Thus, in an example, 0.03 has only one significant figure, that is 3. In 0.0052, it has two significant figures, that is 5 and 2. Rule number 4. Trailing zeros to the right of the number without decimal point are not significant figures. For example, 0.200 gram has three significant figures. But if otherwise the terminal zeros are not significant, there is no decimal point. For example, 1.00 has only one significant figure, but 100 has three significant figures, and 100.00 has four significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 to the power of 2 for one significant figure, and 1.0 into 10 to the power of 2 for two significant figures, and 1.00 into 10 to the power of 2 for three significant figures. Please note the numbers, the zeros, trailing zeros to the right of number, because in all these cases, these are without decimal point are not significant. The powers of 10 are not taken as significant. See here 10 square. See this 10, the powers of the 10 are not taken as the significant figure. Rule number 6. For a number with a decimal, trailing zeros are is significant. For a number with the trailing zeros are significant. For example, 2.308 centimeter can also be written as 0.002308 meters. 23.08 millimeter, it becomes 23080 micrometer. Rules for arithmetic operation with significant figures. For example, for addition and subtraction, the final result should have as many decimal places are there in the number with least decimal places. Example, take 436.32 grams plus 227.2 grams plus 0.301 grams. And here you see after the digit only middle number has one digit. So your answer should also have one digit. So if you add them, we will get the answer 663.821. But the final result should be rounded off to 663.8 because there is only one digit after decimal point in the second term in the given example. In multiplication division, the final result should have as many significants are there in the original numbers with the least significant figures. Here also the number should be same as the least significant figures. For example, density is equal to 4.237 divided by 2.51 centimeter cube. So the answer, if we divide 4.237 by 2.51, we will get 1.69 grams. Here, see in the numerator, there are 3 digits after decimal point, whereas in the denominator only 2. So the answer should have only 2 digits after the decimal point. The answer is 1.67 grams per centimeter cube. The speed of light is also written in the same way as it is rounded off to 3.00 into 10 to the power of 8 meters per second. 1 year becomes 3.156 into 10 to the power of 7 seconds. And 1 light year will be equal to 9.47 into 10 to the power of 5 meters. Rounding of uncertain digits. Preceding digit is raised by 1 if the insignificant digit to be dropped is greater than 5 and is left unchanged if the latter is less than 5. Example, consider 2.746. Now we have to round off this number. So here the last digit is 6. We have to round it off. So because 6 is greater than 5, the previous digit 4, which is even, has to be raised. So that is rounded off as 2.75. And 2.743 is rounded off as, see here the last digit is 3. So if you cancel it, it is less than 5. So it remains 4. So it is 2.74. Next is if the insignificant digit is 5 and the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 5. Consider an example, previous 2.745. So the last digit is to be dropped. So we have to round it off to 2 significant digits after decimal point. So if you want to cancel 5, if it is 5 and the previous is even that is less than 5 and even, then it becomes the answer is 2.74. And in another example, say for example 2.735. So in this case, last digit 5 is to be rounded off. But the previous digit is odd, that is 3 is odd number. So it can be rounded off as 2.74. So similarly, we can round off the speed of light. The original speed of light, actual value is 2.9979245 into 10 to the power of 8 meters per second. So if we round it off to the first digit, then it becomes 3 into 10 to the power of 8 meters per second. You can practice this. So value of pi, as we know, is 3.1415926. We may take the value as 3.142 or 3.14. Accuracy, precision of instruments and errors. Precision refers to the closeness of various measurements for the same quantity, whereas accuracy is the agreement of a particular value to the true value of the result. The accuracy of a measurement is a measure of how close the measured value is to the true value. True value of the quantity. Accuracy is the agreement of a particular value to the true value. Example is, if the true value for a result of 2 grams and the student takes two measurements and reports the result as 1.95 and 1.93. So the students here take this value 1.95 and 1.93 and its average is 1.940. So here in this case, the values are precise but not accurate. It is not close to the actual value 2 grams. So in the second student, that is student B, takes the first reading as 1.94 and 2.05 as the result of two measurements. These observations are neither precise nor accurate. It is neither precise nor accurate because it is far away from the actual value of 2 grams. The student C takes repeats the measurement. The student C repeats the measurement and reports 2.01 and 1.99 as a result. These values are both precise and accurate. So average is 2.00, hence it is accurate. This can be more clearly stood as shown in the table. So the accuracy and precision and accurate are shown above. Precision is the degree of exactness. It tells us to what resolution or limit the quantity is measured. Precision refers to closeness of various measurements of the same quantity. Errors. The difference in true and measured value of quantity is called error of measurements. We will take up dimension analysis. Often while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. Let us take an example. A piece of metal is 3 inch long. What is its length in centimeter? We know that 1 inch is equal to 2.54 centimeter. So therefore, we have to convert it into centimeter. We can write 1 inch divided by, we have to divide it by 2.54 centimeter. That is equal to 1. Or reversing, we get 2.54 centimeter divided by 1 inch is also equal to 1. Both are called unit factors. Similarly, in another example, 3 inch is equal to 3 inches into 2.54 divided by 1 inch. So therefore, that it becomes 3 into 2.54 centimeter or 7.62 centimeter. It should be noted that the above example, the units can be handled just like any other numerical part. It can be cancelled, divided, multiplied, squared, etc. Let us take another example. A jug contains 2 liters of milk. Calculate the volume of the milk in meter cube. Since 1 liter is equal to 1000 centimeter cube and 1 meter is equal to 100 centimeter, this gives the result 1 divided by 100 centimeter is equal to 1 or 100 centimeter divided by 1 meter is also equal to 1. Therefore, for finding Q, we divide 1 meter by 100 centimeter whole cube and that becomes 1 meter cube divided by 100 cube. That is equal to 100 centimeter cube. 1 meter cube divided by 10 to the power of 6 centimeter cube. that is equal to 1 cube, that is equal to 1. Now 2 liters is equal to, given question is 2 liters, 2 into 1000 centimeter cube. So the above number is multiplied by unit factor. So therefore 2 into 1000 cube into 1 meter cube divided by 10 to the power of 6 centimeter cube, that is equal to 2 meter cube divided by 10 to the power of 3, that is equal to 2 into 10 to the power of minus 3 meter cube. So there is a question which we can do it as a homework. How many seconds are there in 2 days? Now we will answer some of the multiple choice questions. Question number 1. Identify the total number of base units and fundamental scientific quantities in SI system. Option A is 5 base units. Option B is 6 base units. Option C is 7 base units. And option D is 8 base units. We know that there are 7 base units, and these base units are meter, kg, second, ampere, Kelvin, candela, and mole. And you please refer section 1.3.3 of this video, and the details are given here. So C is the correct answer. Please mark it. So next question. Match the prefixes present in column 1 with their multiples in column 2. Mark the appropriate choice. So please read the question. Column 1 has the four prefixes, that is A is pico, B is femto, and C is milli, and D is giga. Column 2 also has four choices, four parameter multiples, that is 1 is 10 to the power of 9, 2 is 10 to the power of minus 3, 3 is 10 to the power of minus 2, and 4 is 10 to the power of minus 15. Now to answer this question, you have got four choices, A, B, C, D. For quick answer, you refer to the choices. A is to 1. So we know, select pico. Pico is 10 to the power of minus 12. So you see in the column 2, 10 to the power of minus 12 appears is the third choice. So wherever 3 is there, you just find out. Here the 3 is appearing in option D. So D should be correct answer. You verify. B is 4. What is B? B is femto. Femto is 10 to the power of minus 15. That is also correct. C is milli, 10 to the power of minus 3. So it is 2. This is also correct. And D is giga. Giga means 10 to the power of 9. So it is given here. So option D is the correct answer. Please mark it. Next question. Question number 3. Consider the following figure, the correct relationship between Fahrenheit and Celsius scale. Two scales are shown here. The freezing point of ice and boiling point of ice are shown in the centigrade scale. This is centigrade scale and this is a Fahrenheit scale. So you have been given four choices. Degree F is equal to degree C plus 273.15. B, option B is degree F is equal to 2 by 5 degrees Celsius plus 16. Option C is degree Fahrenheit is equal to 9 by 5 degree C plus 32. And option D is degree F is equal to 1/3 of degree C plus 32. Now refer to the section 1.3.7 and mark the answer correctly. The correct answer is option C. That is degree F is equal to 9 by 5 degrees C plus 32 degrees. Now fourth objective test. Few figures are expressed in scientific notation. Mark the incorrect notation. Option A is 234,000. This is given equals 2.34 10 to the power of 5. So here we have to mark the incorrect. 8008 is 8 into 10 to the power of 3. This is also correct. Now, option C is 0.0048. So if you make it 4.8, it is 4.8 into 10 to the power of minus 3. And option D is 500.5, 5 into 10 square. Here we have to identify the incorrect figure. So it is 4.8, 10 to the power minus 3. The correct answer is 8008 into 10 to the power of 3, because here it should write 8.008. That is not written, and 10 to the power of 3 is also correct. So the wrong number figure is 8008 is equal to 8 into 10 to the power of 3. Mark the rule which is not correctly stated about the determination of significant figure. So you read all the 4 options and identify the wrong rule which is stated here. So option A, all non-zero digits are significant. This is the correct. All the zeros between two non-zero digits are not significant. So this is wrong. So you can mark option B as the correct answer. So this rule is wrongly quoted. Please refer section 1.4.2. Now 6. How many significant figures are present in 0.010100? So we have to see there are 4 options. A is 7, B is 5, C is 3 and D is 10. How many significant figures are there? So the correct answer here is B, that is 5 significant figures. Next question. Identify the correct answer in addition of 3.0223 and 5.041. So numbers are given here. That we have to add 3.0223 and 5.041. If we add, we get the answer as 8.0633. Since 5.01 has only 3 digits after decimal point, the answer should also be 3 digits after decimal point. Hence, the 3 decimal points is 8.6063. You mark the C is the correct answer. You mark it. Next question. Which set of figures be obtained after rounding up the following number up to 3 significant figures? So, 3 significant figures given are 34.216, 0.04597 and 10.4107. So 34.216 can be up to the following 3 significant figures. So option is 34.3, 0461 and 10.4. So you have to analyze it. The correct answer is, you see here, correct answer is B, because now in B, in this number, the 3 significant figures are 342. So it should be 34.2, and the next number is 04597. So if you make it 3 significant feet, it should be 0.046, and the final one is 10.410. It becomes 1, and it should be 10.4. So it is 10.4. It is appearing, all the 3 correct answers are appearing in option B. Hence you mark it. We'll continue and answer some more multiple choice questions. Question number 9. Which of the following option is not correct? Please underline not correct. We have to find the wrong answer. Find the correct answer and wrong answer we have to mark. So here, if you analyze, you will know that the fourth answer is 0.0048, that is equal to 48 into 10 to the power of minus 3. This is a wrong answer. Actually, it should be 48 into 10 to the power of minus 4. The wrong answer, wrong is, which is not correct, is option D. Next question. What should be the volume of milk in meter cube which measures 5 liters? So we have got 4 options. 5 into 10 to the power of minus 3 meter cube. B, 5 into 10 to the power of 3 meter cube. 5 into 10,000 meter cube. And D is 5 into 10 to the power of 6 meter cube. Now we have to calculate. 1 liter is equal to 1000 centimeter cube, and 1 meter is 100 centimeters. Converting, we get 5 liters is equal to 5 into 1000 centimeter cube, and that when we convert it, we get 5 into 10 to the power of minus 3 meter cube. Correct, mark the correct answer. So A is the correct answer. Next question. How many seconds are there in 3 days? We have been given 4 options. Now we have to do actual calculation. So 3 days converted into hours, that is 3 days into 24 hours into converted into minutes is multiplied by 60, and then convert it into seconds is 60 seconds. That we get answer as 2,59,200 seconds. This answer is available as option A. Please mark it. Next question. 18.72 grams of substance X occupies 1.81 centimeter cube. What will be its density? So we have to find the density measured in correct significant figures. Four options have been given. So we have to calculate the density from the question. So density is equal to mass over volume. So 18.72 grams is mass and volume is 1.81 centimeter cube. So that is equal to 10.34 grams per centimeter cube. Since volume has three significant digits, we have to find the answer where three significant digits are available. So it will be, the correct answer is 10.3 grams per centimeter cube. This is the correct answer. With this, we come to the conclusion of Unit 1, Part 2 of some basic concepts of chemistry. In the next session, we will take up Unit 1, Part 3. And there we will cover laws of chemical combinations, Dalton's atomic theory, and atomic, molecular, and masses. Till then, goodbye.